Hi, this video will cover section 1.8 combinations of functions and the composite function. So when we say combinations, just like combining like terms, we are going to be able to combine functions and also using like terms. So that will include adding and subtracting, multiply and dividing functions. Then composition will be slightly different, and it will be when we actually embed one function into the other. So something like f of g of x, or we may use the notation f of g of x. So in this case, the function g is inside function f, but we will go through some examples. We also have, we'll use combinations and compositions of functions to solve some real life problems. So right here we have, we could also refer to those combinations as the arithmetic combinations of functions. Remember, addition, subtraction, multiplication, and division of two functions. So just as as two real numbers can be combined by the operations of that we just mentioned, addition, subtraction, multiplication, and division, to form other real numbers, two functions, or more than two actually, can be combined to create new functions. So that's what we're going to be doing. So we have first our function f right here, f of x, and then we have the other one, g of x. So as you see here, for our first problem, it's going to be the sum of two functions. And so we're going to write whatever is for function f, which will be 2x minus 3. And then we're going to add the other function, which is g, and that is x squared minus 1. Now here, since I'm adding, I don't need to be extra careful with the negative signs, but on the next example, we're going to use parentheses. So now what we do here is we combine like terms. The only two that are like terms will be the -3 and the -1 because they're just numbers, real numbers. The x squared and the 2x are not like terms, so we do not combine them. And then we're going to write it in descending order, meaning that we start with the term of the highest degree and then to the one of lowest degree, which will always be the constant terms. So we start with positive x squared. Then we're going to have plus 2x from here. And then we have -3 minus 1, so that will be -4. And that will be the first example. So the next one is the difference of the two functions. So first I'm going to write down function f, which is 2x minus 3. I'm taking that from here. And then I need a minus, because we're looking for the difference. So minus. And now for function g, which is a two-term polynomial, we are going to use parentheses. It's very important that you do use parentheses, because if you don't, you may forget that you're actually subtracting the whole equation, not only the x squared. So then you have to distribute the negative sign like this. And then we will have 2x minus 3 for the first function. Then after distributing the negative, and remember, it's like you have an invisible -1 outside the parentheses multiplying. So -1 times x squared is -x squared. And then -1 times -1, it was going to be +1. Now from here, we're going to combine like terms. And the only like terms, again, will be the constant terms. But see how we have a +1, not a -1. So we only have -x squared. Then we have a positive 2x. And then we have -3 plus 1 is going to be -2. The next combination is going to be the product of f of x times g of x. So I'm going to enter or write down f of x in parentheses, the equation here. And then for g of x right here, it's going to be also multiplying. So we're going to have parentheses as well. So here we're multiplying two binomials, and so we have to make sure that we distribute them. So I'm going to take 2x and distribute it to here, to the whole binomial x squared minus 1, which is g of x. And then I'm going to take the -3 that you see here and multiply it times x squared minus 1. What I'm doing is just showing you the long way of I know you have heard the word FOIL, so it just represents what I'm writing is the representation of the distribution of the product. So then I'm going to multiply 2x times x squared. That will give me 2x to the third power because we add the exponents of the variable, and then 2x times -1, so -2x. And then here I'm going to have -3 times x squared, so -3x squared, and then -3 times -1, so +3. Now I'm going to combine like terms, and as you can see, I have nothing to combine because my terms with the variable x, they all have different exponents. And if we don't see an exponent, remember that we know there's an implied 1 right there. And in fact, the constant term, it has an exponent of 0. But we will cover that in the next chapter. So now if I write them in descending order, we start with the power of 3, the exponent of 3, and then minus 3x squared, and then minus 2x, and then plus 3. And so that will be the answer to the question, to the product of those two functions. And then lastly, we have the quotient, as you can see here. So we have function f, which is the equation 2x minus 3, divided by function g, x squared minus 1. And that's it. You don't have to do anything else. However, for a rational function, that's how we will call it, because it's a ratio of two polynomials, as you can see here. They're dividing. So this rational function has a domain with two numbers that must be excluded, because if we were to use those x values in the denominator, then we will get a 0. So how will we find those values? So to find the domain of the function, and we did this in a previous section, so we take whatever's in the denominator, and then we create an equation that says that cannot equal to 0. So we could do two things. We could factor it into a difference of squares, or we could take the -1 across and then take square roots. So if I factor it like this, it will be x plus 1 and x minus 1, because this is a difference of squares. Now from here we take each factor, and by the zero factor property we solve for x, so we get that x cannot equal to -1. And also if we take the other factor, x minus 1 cannot equal 0, this will be x cannot equal to +1. So that is how we find the two exclusions from the domain. And if we wanted to write this domain and interval notation, it will be any real number except for those two. So to exclude that, we use parentheses with the -1, and then we use the union symbol to connect from -1 to 1, and then union symbol, and it will be from 1 to +infinity. If I draw this on the number line, we will have 0 here, here's -1, and here's 1. So we want to take everything from -infinity to 1, but we do not include -1, and then from -1 all the way to +1 without including 1, and then from 1 to +infinity. So the other way that I was mentioning to solve the equation, the inequality, I should say, it will be to, you start here and we take the -1 across. So from subtraction, it goes to addition, inverse operations, or negative to positive. Then we take the square root on both sides and you will get that x cannot equal positive or -1. So, one advantage of factoring is that you get both solutions. And if you solve it this way, you may forget that you get two, positive and negative. So that is the only hard part about finding the quotient of two functions, that you have to clarify what will the exclusions will be, or specify the domain of the function. Okay, so we have here a summary of, in general terms, how they will look like. So the representation that you see here for the sum, f plus g of x, it's the exact same thing as the way that we wrote it on our first example. It will be f of x plus g of x. So they have the exact same meaning, whether the plus is here or here. And in fact, that's how you will find them. You just simply add one to the other. Now here for the difference, we see the negative sign here, f minus g. So it will be the same as f of x minus g of x. And it's very important that you understand that the order matters for the difference. So g minus f, it is different than f minus g, because here f is the one that will have the negative sign distributed to every single term inside the function. For product is the multiplication of f times g, so we just simply write one function multiplied by the other function, we perform the multiplication, and that's it. For the quotient, f divided f over g of x is the same as f of x divided by g of x. And of course here we have to make sure that our denominator, which is g of x, is not equal to 0. Example 1, finding the sum of two functions. We have here function f, which is a linear function, 2x plus 1. And then we have g of x, which is x squared plus 2x minus 1. And so what we are supposed to do is to find first the equation for f plus g of x. So f plus g of x equals f of x plus g of x. So we're going to write down first function f, which is 2x plus 1. And then we're going to add function g, which it is x squared plus 2x minus 1. Since we're finding the sum, the addition of two functions, we don't need to be so concerned about using parentheses around our function. So we're going to combine like terms, and we have 2x plus 2x. So those two are like terms because x is to the power 1. And then we also have plus 1 and a minus 1, which happen to be opposites. So they cancel out, they equal to 0. So we're going to have x squared first. Then 2x plus 2x will be equal to 4x. And then plus 1 minus 1, that is just equal to 0. So the final answer will be that. And that is the answer for f of g of x. Now for the second part of the question, we are asked to find when x is equal to 3, what is the value of the function. So what I'm going to do is replace, instead of x, we're going to have the number 3. And so here for this x squared and the other for x, we're going to replace those x's with the number 3. So we will have 3 squared plus 4 times 3. So make sure you get used to, using parentheses is not like so needed here, but it's just good practice. So when you substitute a negative number, you use parentheses around it. So 3 squared is 9. 4 times 3 is 12. And so 9 plus 12 is 21. And that will be the function value. Now, we could have found this by using the definition of the sum of two functions, which will be that, right? So we could also do something like this. F of x, well, in this case, it will be f of 3 plus g of 3. So it's saying when x is 3 in both functions, what will be the result? So if I substitute 3 into function f, it will be 2 times 3 plus 1. And if I substitute 3 here and here in function g, it will be 3 squared plus 2 times 3 and then minus 1. And so I'm going to simplify it. So 2 times 3 is 6 plus 1. 3 squared is 9. And then 2 times 3 is 6 minus 1. So let's see if we get 21. So here we get 10. And then 6 and 6 is 12 plus 10, that's 22. Minus 1, we get 21. So we get the same thing either way. So they do have the same meaning. So now we're going to start with composition of functions. And so with that, we're going to substitute not a numerical value like I did here where I substituted the number 3 for every x of the functions. So what I'm going to do instead of substituting a number is substitute an expression. So for example, if we consider function f that is here, and I ask you find f of 3, you will substitute your 3 here and then square it. And that will be equal to 9. Now, what if I tell you substitute instead of a 3, I give you the letter a. So then the answer will be, instead of x squared, it will be a squared. Also, when we worked with the difference quotient, we had to substitute a binomial, which was x plus h. And so if we do that with that function, it will be x plus h and then square. And then after that, we had to actually multiply x plus h times x plus h. So sometimes we had ways to simplify them even further. So the answer to this one was x squared plus 2 xh plus h squared. Okay, so what we're going to do now is we're going to substitute x with the whole function that comes from g of x. As you could see here, the equation for g of x is x plus 1. So that is what we're going to substitute inside the function f. So we see that function f, it has x squared. So I'm going to open parentheses and substitute the x with the expression x plus 1. Why x plus 1? Because we're trying to find f of g. F of g of x. That is how we read it. So that will be one valid answer, but if you are asked to simplify it even more, you will have to multiply x plus 1 times x plus 1, which will give us x squared plus x plus 1, which will be x squared plus 2x plus 1. if I was to multiply the first terms and then the outer terms and then the inner terms and then the last terms. So we get that, and we read it, we could call it f of g of x. The one that is mentioned second is the one that is substituted inside the other. And we could also call it f composed with g, or do not say fog. That is not an O. As you can see, it's a smaller circle. And so what it means is what I wrote down here. F of g of x. Like that. Now, we could also compose one function into the other. So we could say g of f of x. And what that means is that we will have g, and then f of x will be inside the function g. So that will be read as g of f of x, or it could also be read as g composed with f. Okay, so a quick explanation of how this works is, as you could see here, if we look at the sets of parentheses, the innermost term is the letter x. And so that is going to be the domain of the function that is inside the other. So in this case, we have function g inside function f. And so what happens here is that the domain of g is called x. And so that x maps through the function g. We substitute that x in here. Right here. And from there, we get an output. So that output of function g will be like a y value. But remember how we use function notation, and so an output could also be represented by the name of the function. So in this case, the function is called g of x. So then we get g of x. And then g of x, it is the range of g, the output, but also becomes the domain of f. So because we are finding f of g of x. So then that whole thing becomes the domain of f. And then we map that into the composition. And so here we have another output, but in this case, the output is the output of the function f of g of x. And we could also refer to this as the range of the composition. Okay, so I'm going to show you with the next example. I believe we could demonstrate that. Okay, this will work. So we have two functions. We have function f, which is 2x, I'm sorry, x plus 2, and function g is 4 minus x squared. So for the first composition, we will be finding f of g of x. and f of g of x, which is the same as the f of, the second function that we have here is the one that will be inside the other function, function g. And then, of course, we have function f, the variable x here. So what we will do now is we are going to replace g of x, the function notation, with the actual equation for g of x, which is 4 minus x squared. Why? Well, because that's what it says here, that they're equal to each other. So we take that equation and we enter that in the parentheses. Now, what does that tell me now? That for this x right here that I have, that belongs to function f, I will replace all of that with the equation of function g. And so it will say, instead of x, we enter 4 minus x squared, and then plus 2. And here I just added the parentheses so that you know that I was substituting the x with that whole thing, but we could also get rid of them like that. And then we combine like terms, and so this will be negative x squared, and we have positive 4 plus 2, that will be a plus 6. And so we have that right there, negative x squared plus 6. Okay, now for the second part of this problem, we're going to find g of f of x. And so it's going to be different than the first one. So now, because the second function being mentioned here is f, that is the function that will go inside the other. So f of x goes here. So the function, and actually I don't need the parentheses here. Okay, so now the equation that we're going to replace f of x with is the one that we had up here. So it is going to be, we're going to be replacing this whole thing. Instead of f of the notation f of x, we're going to write x plus 2. Because that's what the equation for f of x is equal to. Now, function g is 4 minus x squared. I'm going to write it down here so I don't forget. 4 minus x squared. So now what we're going to do is that in place of this x here, we're going to replace that with x plus 2. So this is going to be, we have to write everything else besides the x squared. So 4 minus, and then here's where we're going to replace it, and then we need the square. So what we replace there, instead of the x, we enter x plus 2. Now, the x plus 2 is multiplying to x plus 2 because it's being squared. So we have to simplify this a little bit. So notice how I have a negative here. So I'm going to do my whole operation of the two binomials, and then at the end I'm going to distribute the negative sign. So I'm going to have x squared plus 4x plus 4. Now distributing the negative sign to every single term, And here's after combining like terms. So the shortcut for squaring a binomial is that you square the first term, you square the second term, which is the 2, and then the product in the middle, the 4x, is the product of x times 2 and then double. So 2x times 2, 4x. So that is the shortcut. You don't have to use it. You can write it down by yourself, on some scratch paper and then work it out. So now I'm going to distribute the negative sign. So it will be negative x squared minus 4x minus 4. And this is what is going to equal to, as you can see here, positive 4, negative 4 cancels out. So we just have negative x squared minus 4x left. And that's it. That's the answer for part B, which is the composition of g of f. That is the equation. Okay, now we're going to use part B to answer the question, which is what is g of f of negative 2? So meaning that here now the x is going to get substituted with the number negative 2. So here, and we have to follow everything else from the equation. So we have a negative parentheses, negative 2, and then square, minus 4, and then negative 2. So that is the only thing that I substituted, negative 2 and negative 2 in place of the x's that we had here. So we have to take care of the squares first. So negative 2 squared is positive because negative 2 times negative 2 is equal to positive 4. But we have a negative outside here, so it's going to be negative 4. Then here, negative 4 times negative 2 will be positive 8. So now we have negative 4 plus 8 is negative, no, not negative, but positive 4. We could read it in reverse, 8 minus 4, and it will give you positive 4. Okay, so since we do have that example, I want to show you something else. And so, for example, if we had done with the same as with the diagram, we had an x value here, and that was, we will give it the value of negative 2. And so from here, the function is going to map. In this case, it went inside function f first. So this will be f of x. And so the equation for that was x plus 2. So instead of x plus 2, we will enter negative 2 plus 2. So that was equal to 0. Let's just write it down here. F of negative 2. So it was negative 2 plus 2. So f of negative 2 was equal to 0. So that 0 goes here. So that number, the 0, is what maps into the next function, which will be g of x, g of f of x, like that. So then if we find g of 0, we could take the equation for g, which I have it somewhere. Oh, it's right here. So now if we find g of 0, remember 0 because that's what came from here. So if we substitute 4, well, actually I need an equal sign first. 4 minus 0 squared, and the answer is 4. So our equation went from x equals negative 2 to substituting the negative 2 into f, and then we got a 0, and then we substituted a 0 into here. All of this turned into a 0, and if we substitute that into g of x, g of 0 is equal to 4, and that's what we got here. So that is another way to work this out. And the order f of x was first because f of x was the one that was mentioned second here. So what that means is that f of x is the one that goes inside g of x. Okay, so we're almost done with this section. And we have here in example 5, you form the composition of two given functions. In calculus, it is also important to be able to identify two functions that make up a given composite function. For instance, the function h of x, which is here, it's 3x, I'm sorry, parentheses, 3x minus 5, close parentheses, everything to the third power, is the composition of two functions, f of x, which is x cubed, and then with g of x, which is 3x minus 5. So what's happening here is that we're entering function g inside function f, and so it will be something like this. Well, it is f of g of x, which is equal to f of g of x, which is equal to f of the equation of g of x is here, 3x minus 5. And so if we consider function f to be x cubed, it means that everything that we substitute the x with, which is the 3x minus 5, that will be the raised to the third power. And so that is, it could be called decomposing functions, or decompose a composite function. And so, yeah, this is a good skill to have. And we called inner function, again, is always the one that is mentioned second in the composition. That's the inner function. And here f is the outer function. Okay, so we have the application, and I just want to tell you that I do like this problem a lot. I find it very interesting. I don't know if you grew up in a family like mine where my grandma will never let us put food from that was hot or still warm in the fridge because she will say that the food was going to go bad. So, you know, that was my grandma, or is my grandma. She's still alive. But in reality, once I grew up, I learned that that is not true, and that food, it actually, it's like a more welcoming environment for bacteria when the temperature is not too hot and not too cold. So if you leave your food out so it could just cool down and you can enter it, put it in the fridge, that is the time where the bacteria will grow there. So that's what this problem talks about, and you know, I might have it on my exam in the future. So please try to learn it. So we have the number n, capital N, of bacteria. And if you notice, n is the actual name of the function. So instead of using f of x, we're using n of t. And here we have capital T and lowercase t. So capital T is the input for function n. So if you notice here, t, capital T, is in the equation. And that one represents, that particular equation represents the number of bacteria in a refrigerated food is given by. And so if you keep reading, it says that T is the temperature of the food in degrees Celsius. And so that food is going to be from 2 to 14 degrees Celsius, including 2 and 14 because we have the equal part on the inequality symbol. So input for the function n is capital T, which is the temperature of the food in degrees Celsius. Then if we continue reading, it says that when the food is removed from refrigeration, the temperature of the food is given by the equation. Now that T, capital T, becomes the name of the other function. And now, so capital T is going to be for temperature. And then lowercase t, I'm going to highlight it here, is for the time in hours. So lowercase t is the time in hours, and it goes from 0 to 3 hours with the including 0 and 3. Okay, so again, n represents the number of bacteria in a refrigerated food, and capital T is the temperature of the food in degrees Celsius, and that temperature can also be obtained when you take the food out of the refrigerator, depending on the time, and the time is the lowercase t. So for part A, we are asked to find the composition of n of capital T of lowercase t. So what that means is that since function t is mentioned, capital T is mentioned second, that means that we have the outer function is n and the inner function is capital T. And lowercase t is the time in hours. That will be the input. So actually, I want to show you with a diagram how this is going to look like. So we will have t here. This is the time. And then we go here. And then this is going to be the temperature. And this will be T of T. And then from here, we will move on to the number of bacteria. And that's going to be given by n of T of T. That looks a little ugly. Let's fix that. So T of T. There we go. So we're going to have the inner function, the temperature function. So the equation for that is going to be all of this here. So instead of T of T, we are going to replace that with the equation for T plus 2. All right, now we're going to look at function n. And so for the capital T here and capital T here, we're going to replace those with the equation for T plus 2. So we have 20 times 4T plus 2 square minus 80. And then instead of T, we have 4T plus 2. And then finally we have plus 500. So if we simplify this, first we need to calculate the square of this binomial. And just so that we're all clear on that, it's 4t plus 2. So if we square it, we're multiplying the binomial by itself. So 4t times 4t is going to equal to 16t squared. Then 4t times 2 is going to equal to 8t. Then we have 2 times 4 is going to equal to 8. And then 2, I'm sorry, that's completely wrong. 2 times 4t is going to be equal to 8t again. And then 2 times 2 is going to equal to 4. So if we combine the 2 in the middle, you notice is twice the product of 4t times 2. So 8t times 2 is going to be 16t. And then here we have 16t squared and then plus 4. Okay, so that will go up here instead of that, but we still have the 20 that we must distribute to. Okay, and then we continue with the minus 80 times 4t plus 2, and then the plus 500. And I'm actually going to use the space below before I answer the question. So we're going to distribute the 20 to every single term inside the parentheses. So that will give me 20 times 16. It will be 320, and of course we need t squared, then 20 times 16. T is going to be 320t. And then 20 times 4 is 80. And then I'm going to distribute here the 80. So 80 times 4t is equal to 320t. And then 80 times 2 is equal to 160. And then we have a plus 500. So I'm going to combine like terms. And we have here 320. Oh, and I did make a mistake right here. Oh, yeah, this is pretty bad. So we see how we have a negative 80. So negative 80 times 4t should be negative 320t. And then negative 80 times 2 should be negative 160. Okay, so continuing here, we have 320t squared. I can cancel out the positive 320t with the negative 1 because they equal to 0. And then for the numbers, I can add 80 plus 500, so that will be 580. And then I'm going to subtract 160. So that will give me 420. And so that will be the equation that answers part A of the question. And that is the equation for the n of capital T of lowercase t, or in other words, the n of t of t. Okay, now question B. It says, find the time when the bacteria count reaches 2,000. And so what we want to remember, we defined capital N as the number of bacteria, right? So what we're going to do is substitute that with 2,000 to answer this question. And then we will use the equation here. (320 t squared plus 420 equals, and just like the question says, 2,000. So that's going to be the equation that we will be solving. Now, to solve for quadratic equation, we could use the factoring method, but before that, we have to make sure or any other way, we have to make sure that the one side is equal to 0. So I'm going to use the space here. And that will be 320 t squared plus 420 minus 2000. And so that will equal to 0. So I'm going to combine like terms here. And I'm going to have 320 t squared. We have 420 minus 2000. So that will be equal to negative 1580. And actually, let's try to do something. So if I take this across, it's going to be positive. So maybe we could divide or something instead of factoring, because we have pretty large numbers. So what we could do is, what if we divide by 320 on both sides? Maybe 1580 is divisible by 320, maybe. Oh no, it's not. Okay, but that's fine. We could also have a decimal, so the 320 divided by 320 cancels out, so we have t squared equals to that number in the fraction. And in fact, I can cancel out a 0 or divide by 10. And now what I'm going to do to solve for t is take the square root, so that we cancel the t and the t square. And so what I'm going to do is enter on my calculator the quotient 158 divided by 32, and then I'm going to take the square root, and I get that t is approximately 2.222 hours. So depending on how WavaSign wants you to enter your answer, I wouldn't round to a 2, because at 2 hours the bacteria hasn't grown to 2000 like the question said. At that point it will still be less. So perhaps round up to the nearest hour, or maybe they want you to round to the nearest decimal, 10th or 100th or 1000th, or maybe you could convert the decimals to minutes. So to do that, you could subtract 2 to that from that number, and then multiply by 60, and I get like about 13 minutes. So it could be like 2 hours and 13 minutes. And so that would be the answer to part B of the question. How long would it take for the bacteria count to reach 2000? And it's approximately 2 hours, 13 minutes, or 2.22222. Okay, so I believe there's one of these problems in your homework, or maybe you will see it again on your exam. So thank you for watching.